So here we would like to show that every sequence has a monotonic subsequence. So by saying monotonic, we mean either increasing or decreasing. And we will first get started by defining a subsequence. So if an, and let's emphasize the indices that we use here, is a sequence of real numbers. Actually, here it seems to me that instead of the curly brackets, we should be using just parentheses. So if an is a sequence of real numbers and n1 less than n2 less than n3 and so on is a strictly increasing sequence of natural numbers, then the sequence an sub k for k and n is called a subsequence of an. So let's see what we're doing here. It's as if you start with a sequence and so on, and you choose just some of its terms. And the way the choice is made, or a way to make such a choice, is by choosing the indices of the terms that we want to keep. So the first index that we want to keep here is 2. Then we have 3. Then we have 6. Then we have, and 4 will be 7. Then we have 10, and so on and so forth. Okay, so basically we're specifying that out of the terms of the sequence, we keep infinitely many of them, and we relabel the sequence by AN1, AN2, AN3, AN4, AN5. And of course, we understand that AN1 is A2, AN2 is A3, AN3 is A6, AN4 is A7, AN5 is A10, and so on and so forth. So that will be called a subsequence of AN. So basically the rising sun lemma, which is what we're going to show, says the following. Every sequence of real numbers has a monotonic subsequence. And the proof is really interesting, really pleasant. And let's see why we call it the rising sun lemma. So let AN be a sequence of real numbers. we will call a natural number and a peak index for this sequence, we mean, if am is less than an for m greater than n. Okay, so to understand what this means visually, if we were to sketch the graph, plot the graph of the sequence, I mean, we don't usually plot graphs of sequences for a very simple reason, because they just consist of isolated points. They don't look that interesting. But if we were to do that, and we would get a picture like this, then a term will be called the peak index. So let's say that the number 5 is a peak index. If we imagine that we build mountains that have their peaks on the terms, on the points of the graph, and we imagine a rising sun at positive infinity, then the only peaks that are going to be to have light on them from the sun are exactly the peaks that correspond to peak indices. Okay, because for other peaks, there will be something in front of them that will hinder the light from getting to them. So for example, look at this peak right here. It has this larger term in front of them and no light will be reaching it. Okay, unlike 5, that the light will actually reach it. So these are the peak indices, and there are two cases. Either our sequence has, either there are infinitely many peak indices for our given sequence, or there are finitely many. So let's look at the two cases. So case 1, suppose there are finitely many peak indices for an. So let n1 a natural number greater than all the peak indices. This means that n1 is not a peak index. Hence, n1 is not a peak index. And what does that mean? That means that there is a term of the sequence which is greater than or equal than n1 that comes an1 that comes after an1. So therefore, there exists n2 greater than n1 in n with an2 greater than or equal to an1. And now the story continues. So n2 is not a peak index either. So there exists n3 greater than n2 in n with an3 greater than or equal to an2. Continuing this way, we obtain an increasing sequence, subsequence, an sub 1 less than or equal to an sub 2 less than or equal to an sub 3, and so on. Okay, so we found the monotonic sequence in this case, and then we turn to case 2, which is even simpler. Suppose that there exist infinitely many peak indices for an. And here they are, n1 less than n2 less than n3 less than n4, and so on. Then, by the definition of a peak index, we know that we're going to have an sub 1 is greater than an sub 2, is greater than an sub 3, and so on. So we get a strictly decreasing subsequence. So in the case that we have finitely many peak indices, we get an increasing subsequence. In the case that we have infinitely many peak indices, we get a strictly decreasing actually subsequence. So there is a monotonic subsequence no matter what. And that includes our rising sum lemma. I hope you like that. Thanks for watching.